Hello everyone. So here are your notes for 10.6, segment relationships in circles. The first theorem that we're going to go over is called the segments of chords theorem. So we're going to be working with only chords in this theorem. What it says is that if two chords intersect inside a circle, then the product of the lengths of the segments are equal. Now, this word product is the answer to a multiplication problem. So when we see this word product, we're going to be multiplying some numbers and values together. What we're going to multiply are these. So taking a look at our picture, we have two chords. I have chord A, B, and I also have chord C, D. Now, these chords have parts to them because they intersect at E. And so we call these parts right here segments of chords. It's really just a fancier way of saying that these are parts of a chord. So if you wanted to take a quick count of how many segments of chords we have AE, we also have EB, and then on the other chord I have DE, and I have EC. So we have a total of 4 segments of chords in this picture. Now, what the theorem says is that if you take the product, in other words, if I multiply the segments of the chords, so I can go ahead and I can take AE and I can multiply it with the rest of the chord, EB, and this should be equal to the parts of the other chord, which is DE times EC. So once more, you take each individual parts of your chords, your segments of the chords, and you multiply them together, and they should be equal to the product or the other segments multiplied as well. All right, so let's go ahead and take a look at example 1. It says to solve for the length of ML. Now, when I take a look at ML, I notice that I don't have any actual measurements for either the entire length or each individual segment. But what I do see is that ML intersects KJ, which is another chord. So because I have two chords that intersect each other, I can go ahead and use the theorem from earlier, which says that if I go ahead and I take the segments of one chord, so let me go ahead and take MN and multiply it with NL, this product should be equal to the product of the segments of the other chord, which is Kn times Nj. So now all we need to do is substitute in. Mn is going to be labeled, going to be substituted with x plus 2. NL, I know it's a little bit messy and crowded down here, but NL is going to be x plus 1. And this will be equal to Kn, which is here, x. And then Nj is going to be x plus 4. So we have Kn, which is x, times x plus 4. All right, now, on the left side of the equation over here, I have two expressions that need to be multiplied. And when we see this, you can either FOIL, which is doing or multiplying the first terms, the outside terms, the inside terms, and then the last terms, right? That's FOIL. First, outside, inside, last. Or you could go ahead and you can just draw arcs or rainbows. And I'm going to go from the first term to the first term in the second expression, x times x, that gives me x squared. And then I will go from x to 1. That becomes 1x. And then I have 2 times x, so plus 2x here. And then 2 times 1, that's just another plus 2. This is going to be equal to. On the other side of the equation, I also have to distribute. But because I have one expression and one variable, I only need to distribute the x to the 2 terms on the inside. So we get x squared plus 4x. Okay, now, from here, what I see is that we have x squareds, and we have a couple of terms with x's. Let's go ahead and let's actually combine our like terms on the left side and rewrite the equation first. So we get x squared. X plus 2x gives me a total of 3 x's. Plus 2 is equal to x squared plus 4x. From here, there are actually several ways to solve, and it really doesn't matter which way you go. We're all going to get to the same answer at the end of the day. But here's what I see. Like I said, I see that I see x squared terms. I also see x terms. My mind is kind of going towards quadratics, so I'm going to see if I can collect all of my terms on one side of the equation first. So I'm going to kind of do 2 steps in one. I'm going to subtract x squared on both sides of the equation. And when I do any sort of operations where we're moving one term to the other side by doing the opposite operation on both sides, I want to make sure that I write it underneath its like term if it has a like term on the other side. So what I mean by that is I'm subtracting x squared on both sides, and so I'm going to make sure that I align this x squared with its like term. I can also go ahead and I can subtract 4x on both sides of the equation here as well. And here's what we get. X squared minus x squared, this actually becomes 0. And plus 4x minus 4x, this also becomes 0. So on the right side of the equation, we just now have 0. On the left side of the equation, I have another x squared minus x squared. This also becomes 0. And then plus 3x minus 4x leaves me with a negative 1x plus 2. And then from here, we just need to quickly solve for x by subtracting 2 on both sides of the equation. And we end up with negative x is equal to negative 2. But because I do not want to have a negative x, or rather, we're not technically done yet, I need to make sure that I divide by negative 1 on both sides so that we can turn this into a positive 1, or get rid of that negative coefficient. So we get a positive x is equal to 2. Now, we need to go back to the problem one more time, though, because it's asking us to solve for the length of ML. And I'm technically not done because I just solved for x. So in order to solve for ML, I need to actually add together its segments, which are MN and NL. So substituting n, ML is going to be equal to x plus 2 plus x plus 1. You could, if you would like, combine like terms right now, but because I already know what the value of x is, I'm going to go ahead and substitute that in. So we get 2 plus 2 plus another 2. So I needed to substitute it in 2 2's because I have 2 x's plus 1. And then adding this all together, we find that ML is equal to 7 units. All right, so go ahead and pause the video here and see if you can give this one a try on your own. Alrighty, so go ahead and double check over your answers. Again, using that theorem, I went ahead and multiplied the segments of my chords and set it equal to the product or the multiplication of the other two segments of the other chord. And then just doing some quick algebra, we went ahead and finished up to find that x is equal to 5. Now, one small reminder, when you substitute in an expression, you need to make sure that you use the parentheses. And then not just that, but when we multiply, we need to make sure that we distribute this too to both of the terms inside of the expression. All right, let's go ahead and take a look at our second theorem now. The second theorem is called segments of secants theorem. The theorem we were working with before had to do with chords inside the circle, but the second one deals with secants. How do we know when we have secants? This is when we have a line, or I guess in this case, a line segment that intersects the circle at 2 points. Now, in order to use this theorem, there must be two secants, and the secants must also have a common exterior point, which in this case is point E. Now, here's what the theorem says, though. It says that if you take the external segments of the secants, so segment EA is an external segment of secant AB, and segment EC is also an external segment of secant ED. They are, of course, called external segments because they are literally on the outside of the circle, hence external. Now, what do we do with these external segments? We take their lengths and we multiply them with the whole secant. And this should be equal to the external segment of the other secant times the whole other secant. So what does that look like? If we take, again, the external segment AE, or EA, and we multiply that with the whole secant, in other words, EB. This should be equal to the other external segment, which is CE, and we can multiply that with, again, the entire segment ED. And this should be equal to each other. All right, so let's go ahead and let's actually use that in an example now. So for example 2, it says to solve for the value of x. So x here represents the length of ST. And first thing that we notice is that we are not working with two chords that intersect inside the circle. Instead, we are working with two secants with a common exterior point. So we're going to go ahead and use that last theorem that we just went over. So let me go ahead and rewrite the words here. We need to take the external segment of the secant, and we need to multiply it with the whole secant. So let's go ahead and let's take RP, which is the external segment of secant RQ. So that's what I'm going to multiply with, the whole secant. This is going to be equal to the external piece for RT, which is RS. And I'm going to multiply this with the whole secant, which again is RT. Now, let's go ahead and let's carefully substitute in. RP is 9 units long. But when I multiply it with RQ, keep in mind again that RQ goes all the way from R to Q. So if I want the whole length of RQ, I need to take 9 and I need to add it together with PQ, which is 11. And this is going to be equal to RS, which is 10. And for RT, I need to do something very similar. If I want the whole length of RT, then I need to take RS, which is 10, and add it together with ST, which is X. So it might look a little bit funny, it might look a little bit weird, but again, it's because I don't know what X is. So in order to find the whole length, again for RQ, I added together 9 and 11. So same thing for RT. If I want the whole length of RT, I just need to take 10 and add it together with X. All right, so on the left side here, I can go ahead and combine the like terms, which are 9 and 11 on the inside of the parentheses. This gives me 20. This is going to be equal to, and I need to distribute this 10. So 10 times 10 is 100, and 10 times X is going to be 10X. 9 times 20 is 180. This is equal to 100 plus 10X. All right, from here on out, it is all algebra. Let's go ahead and subtract 100 on both sides of the equation. And we get 80 is equal to 10X. Last but not least, divide by 10 on both sides of the equation. And we get that 8 is equal to X. And there we have it. All right, go ahead and pause the video here and see if you can give this one a try on your own. All right, go ahead and double check over your answers once more. The segments here weren't labeled, but the external pieces were 5 and 6. But keep in mind that we needed to multiply with the entire secant for each side. So we needed to add together 6 and 9. And on the other side, we needed to add together x plus 5 or 5 plus x. And please make sure that you remembered to distribute. All right, let's go ahead and cover our third and final theorem. It's called segments of secants and tangents theorem. So in this picture, we should have both a secant and a tangent. And we do. We have segment ED, which is a secant, since it intersects a circle twice. So ED is a secant. And then we have EA, which is a tangent, since it only intersects the circle once. Now, what this theorem says is actually almost very similar to the previous theorem that only had secants. We take the external segment of the secant and you multiply it with the whole secant itself. So I'm going to go and write it in words. We take the external segment of the secant and you multiply it with the whole secant. And what this is equal to is actually the tangent squared. So let's go ahead and let's actually use the names of the parts that we see in the picture. So the external segment is going to be EC. And we are going to multiply it with the whole secant, the entire thing, which is ED. And this should be equal to the tangent, which is EA. And we need to square it. All right. So let's go ahead and let's use this in an example. Example 3. We need to solve for the length of RS. So here is RS in red. They've already gone ahead and labeled it as X for us. So from the previous theorem, it tells us to take the external segment of the secant and we need to multiply it with the whole secant. And this should be equal to the tangent squared. So the external segment is RS. Again, it is because it is the segment that is on the outside of the circle, hence external. And I'm going to multiply that with the entire segment, which is RT. And this will be equal to RQ squared. Now that I have our geometric equation, we can go ahead and just substitute in. So RS is going to be X. And RT, keep in mind again that to get the whole length of RT, I need to add RS, which is X, together with ST, which is 8. So I need to add X plus 8 to get RT. And this will be equal to 16 squared. All right, so distributing here, X times X is X squared. X times 8 is a positive 8X, so plus 8X. This is going to be equal to 16 squared, which becomes 256. All right, now from here, it looks like we have a quadratic because I have an X squared term. I also have an 8X, and I have a value or just a number at the end. So what I would like to try and do is see if I could factor or possibly use the quadratic formula. But before I do that, I need to make sure that one side of the equation is equal to 0. So we can quickly do that by subtracting 256 on both sides of the equation. And what we get is X squared plus 8X minus 256. Again, we kind of write this minus 256 just kind of as a third term because there are no like terms on the left side of the equation. And then we just go ahead and set this equal to 0 because, again, 256 minus 256 is 0. Now we can go ahead and see if we can factor. But unfortunately, there are no factors of negative 256 that will add to give us a positive 8. So what we need to do now is we need to use the quadratic formula. Here is what the quadratic formula says. It says that if you want to find x, or if you want to solve for x, x is going to be equal to negative b plus or minus the square root of b squared minus 4 times a times c. All of this gets divided by 2 times a. Now, if you're unfamiliar as to where these a, b's, and c values come from, I'm going to go ahead and link the quadratic formula video below. So go ahead and take a moment to watch that if you need to. But let's go ahead and we're going to substitute directly into this quadratic formula. Our a value, because there is no number in front of x squared, it is technically an invisible 1. Our b value is a positive 8, and our c value is a negative 256. So once more, substituting this all in because our goal is to find x. X is equal to negative 8 plus or minus the square root of 8 squared minus 4 times 1 times negative 256. All of this gets divided by 2 times 1. All right, so what I'm going to do here is I'm going to, just like in the quadratic video, I'm going to work inside of the square root first. So I have 8 squared, which gives me a 64. I'm going to go ahead and multiply 4 and 1. That gives me 4. And then 4 times negative 256 gives me a negative 1024. Again, I choose to ignore this minus sign for now and just take care of the numbers and only take care of the positives and negatives of A or C first. So this minus sign just comes along when I rewrite the equation. All of this lives inside the square root, and I haven't done anything on the outside, so let's go ahead and rewrite everything that was on the outside. So I had a negative 8 plus or minus the square root. All of this was getting divided by 2. And this, again, is all equal to x. All right, finishing up inside the square root, we get that x is equal to negative 8 plus or minus the square root of 64 plus 1024. All of this gets divided by 2 still. This becomes negative 8 plus or minus the square root of 1088, all divided by 2. All right, from here, what we need to do is we need to simplify our square roots. Again, if you don't remember how to simplify your square roots, I'm going to go ahead and link the video for that down below. Please take a moment to watch that if you need to review. But I'm going to go ahead and skip right to the simplifying of the square root of 1088, which is 8 times the square root of 17. All right, the last thing that we need to do here is we need to double check to see if our denominator can simplify both of the terms in the numerator. In other words, can 2 divide negative 8? Yes, it can. Can 2 divide this 8 here outside of the square root? And yes, it can as well. So I can actually go and do one last step, which is to simplify by dividing all of the terms in the numerator with this positive 2. And here is what we get. We get that x is equal to negative 8 divided by 2 is a negative 4. Plus or minus 8 divided by 2 is just a 4 times the square root of 17. Now, this technically would be our final answer if we were working in algebra, but because we are working in geometry, let's come back to the picture for a moment and remind ourselves what we were solving for. We were solving for the length of RS. And the length of RS, the smallest it can be, is 0. We cannot have a negative distance, a negative length. So when we take a look at our values down over here, I notice that there is a possible value where it says negative 4 minus 4 times the square root of 17. Unfortunately, that would give us a negative number, a negative length. So I cannot use the negative, which means that I only have one answer, which is x is equal to negative 4 plus 4 times the square root of 17. And that right there is our final answer for example number 3. So kind of a lot to do here, but it was mostly due to the quadratic formula. And again, if you need a review on the quadratic formula, go ahead and watch the video down below. All right, go ahead and pause the video here and see if you can give this one a try on your own. All right, go ahead and double check over your answers. This one did not require the use of the quadratic equation because we only have an x squared term and there are no x terms. and we just have a value. So what we do instead to solve is to just square root both sides so that we can go ahead and cancel out the square root and the squaring. And so that leaves us with x is equal to plus or minus 2. Now, I didn't stress this necessarily, but just keep in mind that when we do square root a number, it technically gives us a positive and negative value of our answer. But because x represents distance or a length, it cannot be negative. And so our very final answer is a positive 2. All right, that's it for this video. Thank you so much for watching.